Hey, good afternoon, everyone. This is Celso Batalha for Green Valley College, and um, this is Astronomy Online. Let me share screen. There you go. And in particular, this week we are focusing on the laws of motion, orbits, and gravity. In fact, we will discourse primarily on the effects of gravity, the importance of it to maintain and to constrain the systems that we are used to. Like um, I'm sitting in a chair, right? Why am I sitting in a chair? If I stand up, why don't I go in orbit? Why do I keep it bound to the floor? And the reason to that is there is a force of gravity. Um, and looking at what happened this weekend, on Sunday we have a solar eclipse, an annular solar eclipse, and I mail all of you about it. And which precedes the solar eclipse we'll see in Oregon in August. That's also going to be a solar eclipse. And this one in the South America, visible in South America, was an annular solar eclipse. So basically, Earth goes around the sun. We learned that in chapter 2. And the moon goes around Earth. We learned that in chapter 4. And so why it goes around, what keeps them together? I know if you take a string, I have a bunch of keys. So I have some cord connect to a bunch of keys, and my keys spin around. Why is that? Well, because there is a tension um, holding these keys in place, and they just keep on going around. And what is the force that keeps the moon going around Earth? What is the force that keeps Earth going around the sun? And what is the force that keeps the sun going around the galactic center? And what is the force that keeps all these 200 billions and so stars orbiting and bound to this big system we call galaxy? And what is the force that keeps galaxies in our local group of galaxies? In fact, it's a poor group of galaxies, few dozen members. What is the force that keep them all together? Pretty much gravity force. Um, so this is the main point of this chapter, and also the main point indicating what are the orbits, the type of orbits planets go, and what type of path the planets go as they orbit the sun. So we are introducing the word elliptic, ellipses, and elliptic orbits. So, but before going there, let me go over the seed, the seed of today's, or in fact, this week Astro News. So, if you go and you read about the Big Bang, and that's the point of the article, and you have to give a summary of what the article is all about and what sort of instruments were used to come up with the knowledge. And there is a third one, a third part that is seated in this type of chat rooms. And so here it is. One of the aspects of the Big Bang Theory is to explain how the universe came about, first of all, and also what type of stuff was present when the Big Bang occurred. And when we think and talk about stuff, we can't help thinking about atoms. So, which atoms were present in the Big Bang? In other words, if you look around, we are surrounded by materials, and these materials is pretty much build up on what we call baryonic matter. So, protons and neutrons, and also lighter type of material, electrons. And these protons and neutrons and electrons make up atoms. And since very early in our academic career, in middle schools and high schools, we learn about atoms. hydrogen, helium, lithium, beryllium, and so on, so on, so on. And so where all these atoms came from. Now, we learn as you read about the Big Bang Theory, not the show, but the theory of Big Bang, we learn that in the very past, there was a moment in the history of our universe where all the material, energy, and everything we know were concentrated in what we call singularity. And out of it, expansion took place, and here we are, 13.7 billion years after. So the question is, what elements can be considered cosmological? And I know we haven't studied this yet, but it's a point for you to do a research. So see the question, what elements are cosmological, first of all? Second, later on in our course, we are going to deal with stellar evolution. So stars are not points of light out there we see at night that came out of nothing and pretty much live a static life without any major change. In fact, these stars, they are formed out of something. We will learn. They evolve and they produce something. They are factory producing something, and then they change. We call die. I mean, I know death is a word used for biological system, and stars are not biological systems. They don't get together and make baby stars, but we use the word star death to indicate the processes by which stars stop being what we call stars. They become something else. They become black holes. They become white dwarfs. They become planetary nebulae. They disperse material in the interstellar medium. So the question is, which atoms are formed in stars? They are termed red giants. So what are the atoms formed in red giants? Not red supergiants, but in red giants. So a quick one, I have this is a professor, Linka, she passed that to me, and I thought it was pretty cool. You can take a look there. That might help you to start thinking about it. I have the astrophysical sources of all these atoms, and they are color-coded, so you can kind of go around and figure things out. And also, there are some biological use, color-coded biological use of some of these atoms. So you can use this as a way to initiate your research. Okay. All right. So let's go over our sequence of slides today. Before I do that, let me show you one thing here. See these images? They are awesome images of galaxies. And so here's a spiral galaxy. So think about 300 billion stars in it. And just ask your imagination to conceive planets, the number of planets available in there. So as you can see, all these systems seems to be organized in such a way that rotation takes place. So you have an orbital motion of stars around this galactic center. So what support and what holds the stars in place? Gravity force. So another example of galaxy, the elliptical galaxies here. So elliptical galaxies are galaxies that have a different stellar population than elliptical spiral ones, and they don't have dark lanes indicative of dust. They don't have that. And the gas in between stars, the interstellar medium in elliptical galaxies tend to be hot, very hot, which might indicate how the history of what existed, what preceded the formation of these types of galaxies, as opposed to spiral, as you see in this picture over here. There are some dark lanes indicating dust, the presence of dust and dust to be formed the required cold gas. But regardless if we talk about spiral galaxies or elliptical galaxies, this is a beautiful spiral galaxy, or elliptical galaxy, this one. So there are forces that keep the stars bound to the galaxy itself, preventing them to go away. And this force is gravity. So gravity can be seen in the realm of galaxies, in the realm of systems of hundreds of billions of stars. Now let me show you the Starry Night software. There you go. So this is the Starry Night software. Let me see if I can get solar system, inner planet. Okay, so taking a look. Why didn't go? Taking a look at our solar system, in fact, we are looking at an Earth-centered view of the solar system. So we are basically looking down on Earth and seeing all the other planets going around. So this is not what I want to show. Sorry about that. Solar system. There you go. That's what I want to show. Okay, that is our inner solar system, and you have the sun in there, and you have the terrestrial planets, Earth, Venus, in fact, Mercury, Venus, Earth, and Mars. And you see this cloud of asteroids going around. See that? So why they keep bound? I mean, you don't see strings connecting any of these objects to the sun. Orion is beautifully displayed here. See that? So you don't see any strings connecting them to the sun, but there is an invisible force connecting them. So how to explain this force? And we go over that, and we call that force gravity. Now let's go out. And check the outer planets. So if you go to outer solar system, now we don't see the terrestrial planets anymore because they are too crunched next to the sun. They don't appear in there. But as you can see, Uranus and Jupiter and Saturn and Neptune, they all keep bound and connected to the sun as if they had a string connecting them to the sun. In fact, there are no strings. And again, that is the force of gravity. Interesting enough, you can see that they all go around the sun in the same direction. We call that direction prograde direction as we look down from north celestial pole on our solar system. We see them going counterclockwise. That's the dominant motion. We learn in chapter 2 objects in our solar system go through as a result of see that the same direction is counterclockwise as a result of them, the planets and the asteroids and most of the satellites, they were formed out of material that existed in a circumstellar disk surrounding the sun, and out of that material then the dust, and it's all built up in planetesimals that later on gave rise to planets and satellites, and that's why they all share the same direction of motion. But again, gravity plays a major role. So gravity is what keeps them together, keep them stationary with respect to the sun. Oh, there is something weird. Look at that. What is that? Let me stop here. Can I swap? No, I don't know what it is. Oh, there you go. Oh, I was seeing projection. That's what I saw. Oh, it's an asteroid. It was seeing a weird position. It seems that was going against the flow. They all go in the same direction. All right. Okay. So let's take a look at gravity and following our material. Tycho Brahe. So Tycho Brahe was one of the most ingenious observers of all time. Perhaps Hubble can also be considered an excellent observer and meticulous one. And thanks to Tycho Brahe, in fact, Tycho Brahe, as we studied before, there was two major worldview. One is this Earth-centered worldview we call, let me see if I can bring my marker, if I can talk about it. Can I bring this? I think I can. There you go. Do some annotation. There you go. So two different types of worldview: the geocentric worldview. Earth is in the center, and we thought that all the planets were going and the sun were going around Earth, like we saw in the Starry Night software. In this display, it's right here. See that? So see the Earth kind of stationary and immovable in the center of the solar system with the sun going around. I mean, this view arises if we could move Earth in space. In a way, you are, let's say, you take from Earth perspective, you're not moving with respect to Earth, and then you see everybody else going around, and that is the perception we drive. That Venus and the Sun and Mercury does these little tricks and prograde and retrogrades, as you can see. So Venus now up here is prograding, and now it's still prograding, and it's still prograding, and now it's gonna retrograde. Look at that. See, retrogradation. And when Venus going retrogradation becomes bright with respect to Earth. So all of that was a geocentric worldview, and is a blank representation of what we see in the sky. Now, this is far from truth. It gives results, but it's far from truth, because the truth is the sun is in the center of this solar system, right? And this is the so-called heliocentric worldview, or heliocentric view. Okay. Now, the heliocentric view has the sun in the center. Now, Tycho Brahe, as he started observing with very good detail the planets of our solar system, in particular Mars, he had in fact, he built all his instruments, as you can see here. He was amazing. He had good money. He was very skillful, but he died and he left all his data to Kepler. And Kepler kind of battled his family, but ended up inheriting the data. Tycho Brahe had his own model, cosmological model, which was kind of funny. His cosmological model was Earth in the center, so we have Earth in the center of the solar system, and the sun would go about and revolve Earth, but Mercury and Venus would go in epicycles around the sun. I mean, if you think when Galileo Galilei saw Venus in gibbous phase, this doesn't prove that the sun is in the center of the solar system. It proves that Venus sometimes is further away from the sun than we are, like here. So here Venus goes in gibbous phase, right? And here Venus goes in crescent phase. So Venus is in full phase somewhere here, right? In respect to the sun right here. Anyway, so Tycho Brahe, he was amazing, and he hired Kepler to deal with the mathematical aspects of it. And Kepler was the one who, after Tycho Brahe had passed away, he was able to explain that the orbit of planets around the sun are elliptical orbits. So here's an ellipse. So if you take a cone and then you cut the cone with a plane parallel to the base, you form a circle. If you cut with an angle, depending on how sharp that angle is, you have an ellipse. If it's too open, you might form a parabola and you never close it again. And same with hyperbole. Now, how to build an ellipse? This is interesting. You can do easily with a pencil and two thumbtacks and a circle that is tied around, and then you just go around and then you build your circle. But basically, that's how you do. And x2 over b2, if this is your semi minor axis and a semi major axis. How do I do that? It's the equation, basic equation of an ellipse, and so that's the first law of Kepler. Planets go around the sun in elliptical orbits, and they follow this elliptical path. Now, if you remember the display of Starry Night software, the orbits are elliptical, but they are not so flat as we think about elliptical orbits. Like when we think about comets, we think comets describing elliptical and very flattened orbits. Planets, they go in elliptical orbits, but they are almost, the orbits are not that eccentric. Oops, that's not it. There you go. Now, that's the first law of Kepler. The second law of Kepler is sometimes referred to as equal areas, equal amount of time. Now, when the planet goes around the sun and gets to be near the sun, the speed in which it goes is bigger than it is when further out. Again, is one of the effects of gravity. So the planet is slow down when it's in what's called aphelion part of its orbit, and it goes faster when it's in the perihelion part of the orbit. Now, as a result, it describes a path that is bigger than it is when it's further out for the same amount of time. So let's say you take 1 month and you follow the planet around the sun, and you take this whole path over here. And the same month, when it's in the aphelion part, the path described is much less. But if you connect the planet to the sun, the line connect the planet to the sun will describe an area that is the same if you reproduce this exercise when the planet is in the aphelion. In other words, the planet the line connecting the planet to the sun describes equal areas in equal amount of time. And this is the second law of Kepler. One of the consequences is when the planet is closer to the sun, it's go faster than it is when it's further out. There are several effects associated with that. That has to do with analemma, which is this nice, beautiful position of the sun at noon throughout the year is not exactly always in your local meridian as a result of, first, elliptical orbit, second, as a result of the speed of the planet itself, depending on where it is with respect to the sun. And the third law of Kepler has to do with the time it takes to complete a whole revolution around the sun. Is called sidereal period. And the average distance from the planet to the sun. So the way it goes is the sidereal period to the square is equal to the third power of the average distance of planet to the sun. So Kepler was able to find that these three laws of motion pretty much obey the motion of all planets that were known in those days. And then he stated his laws of Kepler in the 1600. Now Newton came in the 1700, and he, in fact, working on the laws of motion that Galileo Galilei had pretty much worked and developed in the 1600, he was able to come up with his laws of motion. And his laws of motions are basically a little bit counterintuitive. Like the first law of motion in Newton is that if you have a body that is at rest, that body will remain at rest forever and ever and ever, unless something else put that body in motion. Well, this is not so much counterintuitive, but the second law of motion, it is not intuitive. And it says that if an object is moving with a constant velocity, it's going to stay with that constant velocity forever and ever and ever, unless some force acting on it. And if that happens, the second law says that the net force acting on that body is proportional to the change in velocity that body has over a certain amount of time, and we call that quantity acceleration. And the third law of Newton is sometimes referred as the law of equilibrium, and that goes, if a force is exerted on a system, the system reacts to the action with an intensity that is the same value but opposite direction. So that's the laws of action-reaction in Newton's. So putting together these three laws, and we develop them with more property in a physics course, Newton was able to come up with his equation describing the attraction of gravity on all bodies. So the force that connects objects in the universe, objects that have mass, are given by the product of their mass. Let's say I have certain mass. I have 80 kilograms, let's say, and the desk have my computer on has 10 kilograms. So 10 kilograms and 80 kilograms. So the attractive force is equal to a number, which is very small, by the way. It's a very small number, times the product of these two masses divided by the distance of these two objects squared. So when you take these numbers and you plug them in this formula, you realize the attractive force that you have to your computer is much, 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 much less than the attractive force you or psychological force you have to your computer. In other words, the gravitational force of me to the walls in this room I am are almost nothing, are negligible. So my psychology, my volition, my desire to do things overcome that gravity force. It doesn't overcome the gravity force of Earth on me. So Earth is very massive. So think about all the mountains and all the core and the subduction material and layers that goes in Earth's processes. So Earth is very massive, and my 80 kilograms multiplied by a big number here overcome this little number, and that force is significant. And that is what keeps me bound to Earth. And if you, instead of using Earth, you use Earth and Moon here, the mass of Moon, then you can come up with the force required to keep the Moon in orbit forever and ever. And there are other factors affecting that orbit, as we studied before, like the friction between mountains and cliffs with the oceans as a result of Earth rotation and the moon tides, that gives rise to small changes in the moon position as it orbits Earth. Same gravity force is the one that keeps the sun to Earth. So we apply the same formula exactly, including mass of the sun and mass of Earth, distance of sun to Earth squared, and then you have a quantified value for the force that keeps the sun and Earth bound together. And then you can do similar thought process for the entire Milky Way galaxy, which is central part, and then you can find out what is the force, the gravitational force that keeps our planet, our solar system, in fact, bound to the entire group of billions of stars that make up our galaxy to the point we are in the galaxy itself. Okay, so this is pretty much chapter 3. Chapter 3 is a chapter more of physics, but it has this important force. That's the force of gravity, and has also a
alert from system server
important
low battery